Hi, my name is Alexandre from Voxel Labs, and I'm going to talk about a real-time approach for gait analysis using the connectivity sensor for clinical assessment purpose. The human gait can indicate health issues like functional motor ability and cognitive impairment, so a gait analysis can be performed to help physiotherapists plan and monitor the rehabilitation process. And common ways to make this analysis is by using cameras, which often require markers attached to the patient's body and can be very expensive, and making a visual analysis that is susceptible to biased diagnosis. So as an alternative, it may be possible to use the connectivity sensor as a tool to perform gait analysis because it does not use markers, has a low cost, and it is portable. This research aims to create an algorithm that evaluates gait parameters in real time using just a connectivity sensor with the intent of being used in clinical environments for rehabilitation. The real-time aspect here is essential because the physiotherapist can use the Kinect along with the visual analysis during the gait. The algorithm proposed in this research was developed based on different users' gait, recorded by both a golden standard camera and the Kinect. The volunteers were placed at the beginning of a walkway and were asked to stand upright and then start walking at a comfortable pace. We used marks on the floor to predetermine the steps length and the number of steps taken by each volunteer to compare the outcomes and expected values easier. Also, 4 different setups were tested to see how the sensor inclination and distance between the marks on the floor would affect the outcomes. After the gait, the collected data were analyzed in a simulated real-time environment. And based on a questionnaire we applied to healthcare professionals, we chose to analyze the step length, stride length, number of steps taken, stance phase duration, and the angles of the hips, knees, and feet. The analysis starts by getting the joint coordinate and checking if the volunteer's skeleton is being tracked. After that, the Euclidean distance between ankles and all the kinematic variables are calculated. Then we check if a step was taken to calculate the step length, and if it's not the first step taken by that ankle, the stride length is also calculated, and this cycle happens every new frame. The algorithm correctly identified 96.8% of the steps taken during the test, and the Euclidean distance between the ankles was used to identify the steps. When there was a local maximum in the graph, it meant that the user took a step. The graph on the left shows the distance between the ankles in each frame, and the point circled in green represents the local maximum. The graph on the right is a box plot of the number of steps taken in each setup, where the green lines represents the expected outcomes for the setup. The steps length were always lower than expected, but the measurements of this variable were more precise than the ones from the stride length. In both graphs, the y-axis is the value in meters for that variable in each setup, and it is possible to see in the graph on the right that the stride length measures were accurate, but the difference between the maximum and minimum length in most setups was high, and this difference may be related to the cases of false negatives and false positive steps. When measuring the joint angles, only the hips and the knees showed acceptable results, and since the sensor does not recognize the feet well, it presented the worst outcomes. Some examples of angles for each joint during the gait are shown in these graphics, and a moving average filter was applied to facilitate the visualization of the joint's behavior. The first line contained the graphs with the better results and the second one with the worst. Each column represents a different joint. The left one represents the foot, which is calculated using the ankle joint, the middle one the hip, and the last one the knee. The algorithm often failed to identify the stance phase duration for each leg. This variable depends on the knee angles to be calculated, so it is directly affected by the algorithm to calculate joint angles. In conclusion, all the calculations could be done in a simulated real-time environment, indicating that it may be possible to obtain gait variables in real time. The algorithm to count steps worked well, the step length measurements were precise but not accurate, and the stride length measurements were accurate but not precise. And regarding the kinematic variables, only the hip and the knee angles have shown the real joint's behavior in most of the gaits. Feet angles cannot be used for rehabilitation purpose, and also the method to calculate the stance phase duration has to be improved. Thank you.